Okay, so we will use the first few minutes to finish the very end of the last lecture. So first, there are two review questions I want to do. Wait. Please answer the poll question. Okay, thank you for answering quickly. The correct answer is C, is iron. And this is the most heaviest element that can be synthesized in a star's core. Some of you answered carbon and silicon. That's not right. In a low mass star, for example, in the sun, when it reaches the end of its life, we can only, the sun, it's not massive enough to fuse elements heavier than carbon. So at the end of the sun's life, we will just have a carbon star. But if it is more massive than the sun, much more massive, say 10 times more massive than the sun, it will eventually, it can continue to fuse the next heavy elements and like oxygen and neon and all those other heavy elements until it reaches iron. Because iron is the most stable element among all the elements. It cannot fuse anything that is heavier than iron, because fusing iron into heavier elements does not produce energy, but actually absorbs energy. So iron is the most heavy element that can be fused in a star's core. And it can be producing massive stars, not low mass stars. What types of stars end their lives with supernovae? Please answer this poll. Okay, let's see, is an easy question. So I'll just end it now. If you don't answer. Okay, so all of you got it correct. All of you who answered, it is C is the correct answer. Stars that are at least several times the mass of the sun. The sun will not end in a supernova. The sun will end in a white dwarf, and it will stay as a white dwarf forever. For stars that are several times more massive than the sun, it will eventually form an iron core in the center, but the iron core cannot continue to become higher temperature. It will continue to contract in gravitational potential until the electron degeneracy pressure couldn't support it, and the star will all of a sudden collapse into a neutron star. Now, the neutron star will be supported by neutron degeneracy pressure, but it's much, much smaller than the size of the original iron core when it was supported by electron degeneracy pressure, so that the core all of a sudden collapsed into a very, very tiny thing. And so in that process, it produced a lot of neutrinos, and the neutrinos will actually blast away all the outer layers of the star and make a supernovae. So this is what we talked about at the end of last lecture. So we have supernova explosions happening at the end of massive stars. depending on the mass of the star, sometimes they leave behind neutron star, and other times they leave behind a black hole. If it is very, very massive, it will produce a black hole. We'll actually talk about this in our next chapter today. We may not reach neutron star and black hole today, but we'll talk about it next Tuesday. The outer layers of star is just completely ejected in the explosion and can form a very beautiful diffuse nebula. And this diffuse nebula is very rich of heavy elements that are produced in the center of the star by nuclear fusion, but also in the process of the supernova explosion itself. In the process of supernova explosion, there's a lot of energy, and so it can create lots of elements. So here is a periodical table. At the top of it, you have hydrogen and helium, and then some light elements that is very abundant in the universe. For example, carbon, nitrogen, oxygen, these things can be produced in nuclear fusions of stars. And then massive stars can produce several of these heavier elements: oxygen, neon, magnesium, silicon, sulfur. And once you have silicon, you can fuse two silicons together to form iron. And once iron is formed, that's the end of the star. Basically, when it is completely dominated by iron core, then that's the end of the star. So how do you form these other elements? These other elements are formed in other processes, and a lot of them are formed in supernova explosions. But they are much less abundant compared to hydrogen, helium, and these light elements. So here is a plot showing the abundance of elements, basically how much those elements there is in the universe compared to relative to each other, basically. This is, and then the horizontal axis is the atomic number for, actually this is the, that's the atomic number for all the elements. And iron is 26. This is the number of protons in each atom, and that is what indicates different elements. And so hydrogen is 1 and helium is 2, and you can see this y-axis is actually logarithmically spaced. So here is 1. This is, so all these abundance of elements are measured relative to hydrogen. So you have one hydrogen atom, how many helium atoms there are in the universe is about 0.1 compared to hydrogen in terms of numbers. So basically you have 10 times more hydrogen than there is helium. And then you can see that the next most abundant elements in the universe is oxygen and carbon. And these things are 1,000 times less abundant than hydrogen. So that to have one oxygen atom, you need 1,000 hydrogen atoms there. So that every 1,000 hydrogen atoms there is in the universe, you have one oxygen and roughly one carbon, and nitrogen is the next abundant. So these elements, the reason they're most abundant is because they are produced in stars through nuclear fusion. And in both low mass stars and low mass stars can make all the way to carbon, but slightly more massive than the sun, it will be able to make oxygen and nitrogen in the process, and massive stars make lots of these things. And then you can see there these, I think this is neon, and that's magnesium, and silicon, sulfur, and etc. So these are the elements that are produced in nuclear fusion in the centers of stars. And then there is iron. Iron is produced a lot because it's the end stage of the nuclear fusion. So that all these stars that are massive enough, they will produce an iron core. And so, and it's also very stable, so that once you produce iron, it's very hard to destroy it. So that you form a lot of iron in the universe through the nuclear fusion process, but also in the supernova explosion, that many of the remaining elements were able to be fused into iron. But all these other elements, all these heavy elements especially, that are heavier than iron, they're not, they also exist. They're just much less abundant than iron. And a lot of these are produced in supernova explosions, but some of them are also produced in different kind of astrophysical processes, such as neutron capture processes. So those is something to do with nuclear physics. But it's all the elements are produced basically through astrophysical processes, basically. There's a question. The question is, does the atom take the neutron and the neutron turns into a proton somehow? That's right. It's basically that process, so that if you want to produce heavier elements, you have to have more protons, right? So that if a nuclei captures a lot of neutrons, and it will have an internal conversion process that, because you can also, if you turn a neutron into a proton, then it just produce electron at the same time, and then get the electron released, and then you will have additional protons in the nuclei, in the nucleus, so that you change change into a different element, into a heavier element. That's right. A neutron by itself is not a very stable particle. If you just leave a neutron alone by itself, after several minutes, it will actually decay into a proton and an electron and a neutrino by itself. That's called beta decay. So does neutron stars just decay over time? Neutron stars does not decay because it's not isolated neutrons. There is strong force holding them together, and so that they don't, it's a different environment. Okay, get back to this topic. So origin of heavy elements, so that are heavier than helium, where do they come from? Heavier than iron are, I mean, as I showed you already, that elements that are heavier than helium are much rarer compared to hydrogen and helium, but relatively light ones are more abundant. But things that are heavier than iron are even rarer, and they're mostly formed in supernova explosions. And many elements lighter than iron but heavier than helium are formed in nuclear fusion in stars, which then get ejected into space when stars expel their outer envelopes. So then when we talk about origin of the elements, when the sun forms, when the solar system forms, what elements are available to make us, to make the sun, to make the earth, and make us? Those elements have to be coming from the interstellar space, right? They cannot be, even element does not get released from the center of the star into interstellar space, then they will not be available to make the solar system. So what materials are available to make the solar system? They have to be ejected by a supernova explosion into space, right? Into free space. Basically, when a star fuses these elements like carbon, oxygen, and neon and nitrogen, they're locked in the middle of the star. And only when a supernova explodes, these things get through into space. Not only supernova, but also when you have a planetary nebula at the end stage of a low mass star, it will leave behind a carbon white dwarf, but the outer envelopes of the star will be ejected. And some of those outer envelopes are polluted by the nuclear fused elements in the stars, such as oxygen, carbon, and neon. And so some of those elements can also be through into space, but it's just the planetary nebula process or the supernova explosions. They can take the material that are fused in the center of stars and release them into interstellar space. And then once it's releasing the interstellar space, when future generation of stars form, those stars will have planets around them, and those planets will have these heavy elements to form the planet, first of all, and also form different kinds of things on the planet, just like our Earth, right? And so we are all coming from these supernova explosions. So here is the periodical table again, but this periodical table is very different. I can see that it's color coded with the origins of these different elements. And so you see 6 boxes here these colors indicate where does that element actually come from. And here we're talking particularly about the origin of the solar system elements. Sort of in a typical environment like our sun, we can measure the abundance of these elements, and then we try to analyze sort of where do these elements actually come from. Most of the hydrogen and helium, they come from the Big Bang, from the beginning of the universe. When the Big Bang first happened, that hydrogen and helium are formed, and that is most of the helium that is formed there, and all the hydrogen comes from the Big Bang. That's the lightest element ever, right? And then a small fraction of helium are formed in stars. It basically fused from hydrogen into helium and then exploded into rejected into interstellar space through dying low mass stars. That this is the planetary nebula. As you can see, this is a low mass star. It produces more helium and then it dies. It push those helium into space. And then, or exploding massive stars. Exploding massive stars, this is one kind of supernova that we have talked about. And so they will also make some helium, and those helium can be expelled into space. So that you see most of helium come from the Big Bang, but a small fraction of them come from low mass stars, and some of them come from high mass stars. And then you can see these other elements like carbon, nitrogen, oxygen. These things also come from these two kinds of processes. They're basically fused in stars and then exploded and then expelled into space through when a star rejects its outer envelope or when it explodes as a supernova. And you can see that this green color is in a lot of places, and all these elements can be formed in a supernova explosions, but not really heavy ones. Really heavy ones, they are actually through a very different process called merging neutron stars. And actually astronomers have detected these events just recently through gravitational waves. And when two neutron stars merge, they will make a kilonova, not a supernova. It's not as bright as a supernova, so we call it kilonova. And a kilonova explosion will make these even heavier elements. And there's another kind of supernova called exploding white dwarfs. Actually, we will talk about this today. And when you have two white dwarfs, or when you have a white dwarf becoming too massive, they can still explode as supernovas. So that also contribute to some of the elements, as you can see. So this is a process, what we call stellar recycling, or we can call it sort of gas recycling in the interstellar space. As when stars are formed from the interstellar medium, and then inside the stars, they can fuse heavier and heavier elements. And when they die, they return these elements back to the interstellar medium in some ways, right? Low mass stars return it by rejecting the outer envelope, and high mass stars return it by exploding as a supernova. And then once these material get back into the interstellar medium, the component of the composition of it has changed, and the composition become much more rich in massive elements. And then when future generation of stars form, they carry around those elements, and then they evolve, and then they die again, and then return more of these heavy elements into the interstellar space. So the interstellar space gets enriched in heavy elements more and more after each generation of stars. So for example, our sun, the reason that we have these heavy elements in our solar system is because we are not the first generation of stars. We are actually second or maybe third or fourth generation of stars that stars have, some stars have died before they gave us these metals. And that is what formed us. All the elements in our bodies, all those heavy elements, the carbon, oxygen, nitrogen, iron, they are all coming from stars. So we are the children of the stars. So we can say we are star stuff. Okay, that summarizes this chapter about low mass versus high mass star evolution. I didn't talk about the intermediate mass stars because it's more complicated, and it's also sort of in between these two processes, that they can have some characteristics of the low mass evolution and also some characteristics of the high mass evolution. So we're not going to go into that level of detail in this class. So all you need to remember is the tables I gave for the low mass star evolution. Remember that table I made on my lecture slides, and basically low mass stars go through these different stages: mean sequence, red giant, helium fusing star, red supergiant phase, and then it expels its ultra envelope to form a planetary nebula and ends as a white dwarf. Low mass stars evolve very, very slowly, and the mean sequence lifetime takes most of its time. The whole lifetime is billions of years, and 80% of that is in the mean sequence, and a smaller fraction of the time is spent on the red giant phase, and then later stages are very, very quick. You can see that compared to the overall lifetime of the star. And then for high mass star, it also the whole process is much, much faster. The whole process takes only millions of years. Because they're so massive, they burn their nuclear, although they have more nuclear fuel, they're burning it so much faster that they actually can last a shorter amount of time. And again, that most of that time is spent on the mean sequence. They're also burning hydrogen into helium. There is a note here that I didn't really go into detail, which is limited by our time, that in low mass stars, the mean sequence hydrogen burning stage is produced through a process called PP chain. Basically, two protons come together to form a deuterium, and then it eventually lead to a helium nucleus. But in a mean sequence star, in a high mass mean sequence star, there is something called the CNO cycle, the carbon, nitrogen, oxygen cycle. So that if the star is already have some of the carbon, nitrogen, oxygen, it can actually make that the hydrogen burning much faster. So they work like a catalyst in the process, that they get involved in the hydrogen to helium fusion process to make it faster. But the amount of CNO does not change in that process. So the mean sequence is still burning hydrogen into helium. There's a question. Will the universe run out of helium element one day? No, I don't think so. No, as you can, the star formation process is not very efficient. A lot of our hydrogen remains in the interstellar space, and they don't even get involved in star formation. So when a cloud forms a star, it's only turning about a couple % of its mass into stars. A large fraction of the hydrogen and helium just remains in interstellar space. So now even all hydrogen will be turning to helium, and also not all helium will be turning to heavier elements. As you can see, that over many generations of star formation, that the hydrogen and helium are still the most abundant elements in the universe. That the next heaviest element is 100 times less abundant than helium, right? Or 1,000 times less abundant than hydrogen. So these things I think they will almost never run out. Even if you go into an infinite future, in principle, yes, but I think that when when there are too little gas left, that star, they will actually not even collapse and form stars. So you won't run out of these light elements at all. Oops. So mean sequence star, high mass stars will go through mean sequence, and then they will go through many stages of blue supergiant and red supergiant, going back and forth on the HR diagram, but remaining at the top of the HR diagram. They remain to have a very high luminosity, and then they change their temperature back and forth to high and low. When the temperature is high, they are called blue supergiant. When the temperature is low, they're called red supergiant. And they're just burning heavier and heavier elements and building up an onion-like shell structure with heavier elements in the middle, and then a number of burning layers, but a number of fusion shells around it, until the core becomes an iron core, and then it goes through a supernova explosion. And what it leaves behind is either a neutron star or a black hole. So that is single star evolution. One thing that I want to add at the end of this lecture is that how about binary stars? In binary stars, the evolution story can be quite a bit different. In a binary, if two stars are very far apart from each other, then they just evolve on their own with no influence on each other. However, if two stars are too close to each other, when they become a giant, they become so much bigger, right? They can actually influence each other's evolution. And the reason is that the two stars can exchange mass. But before we go into that detail, I want to set this poll question. If you observe two stars in a binary and find that one is a white dwarf and the other is a red giant. So you say you have a binary star and one of them is a white dwarf, the other star is a red giant star. Which star was originally the more massive one? I've launched the poll so you can answer it now. This is should be a more challenging question for you. So there's a question, stars in binary do not have to form at the same time, do they? They actually have to form at the same time. In binary stars, usually they are formed at the same time. Most of the time they're formed at the same time. I mean, the chance of them one star capturing another star and form a binary is very small. So they have to be formed at the same time. Okay, most of you have answered. About half of you chose white dwarf, and then some of you said the red giant, some said they have the same, they were both the same mass, and others say they were, there's no way of knowing. So let's think about this. The two stars have to form at the same time because they're in a binary, right? I mean, that's the case most of the time. Just like in a cluster, in a star cluster, all the stars are formed at the same time. That is sort of the basic assumptions here. And if two stars are formed at different times, then it is very unlikely for them to come together and form a binary. So when you see two stars orbiting each other at small distances, that means that the two stars are very likely to be formed at the same time. So here, that's the assumption. So the assumption is that the two stars are formed at the same time. if you have a white dwarf, that means this is basically the dead bodies of a star, right? That means that star has finished its evolution. And then you have a giant star, that red giant star. That means that star has not finished its lifetime yet. It has finished its mean sequence, but has not finished its evolution yet. And if the two stars are having the same age, because they were formed together, right? They must have the same age. And so so let's say that age is 5 billion years. And if a white dwarf can already be formed within that time, that means that the star that originally, the progenitors of the white dwarf, basically the thing that becomes the white dwarf, the star that became the white dwarf, must be a massive star, a relatively massive star that have a shorter lifetime than 5 billion years, right? And the red giant, since it has not finished its lifetime, that means its lifetime must be longer than the age of the system, must be longer than 5 billion years. So that which star would have a longer lifetime? It's the less massive one would have a longer lifetime, right? So the red giant is the less massive one, and the white dwarf is the more massive one. So B is the correct answer. And half of you got it, right? That's excellent. Because only if it is a more massive one, then it can evolve faster and reach the white dwarf stage first, basically. So that is sort of the basic assumptions, the basic knowledge we have about stellar evolution. But sometimes we can see some very strange examples. For example, in the Perseus constellation, there's a star called Algol, and it is a binary star. And we can measure the orbital motions of the two stars, and then we can figure out what is the relative mass between them. And then we found one of the stars is a 3.7 solar mass mean sequence star. That's Algol A. And then there's another star, it's a red giant star, but it's only have 0.8 solar mass. So you see, is this strange, right? A red giant phase is a more evolved phase in the stellar evolution. So if two stars have the same age, the red giant one must have evolved faster, right? And so, but how can a low mass star evolve faster than a high mass star? That is contradictory to what we have learned, right? So what could have happened? So that is a puzzle to astronomers when we first saw this, but then we figured out what is the reason. The reason is the star can actually exchange some mass. Why can they exchange mass? So if two stars are relatively close to each other, and that is the case in the Algol binary system in Perseus, and the two stars are very, very close to each other, they're actually eclipsing each other. And which is how we can measure their orbital period and etc. So when the two stars are very close to each other, there is a special curve around the star called the rho slope. What is the rho slope? This curve is like the equal altitude line in geography. For example, if you're trying to describe a mountain on a map, on a geographical map, you want to say where is the peak of the mountain, you would use these contour lines to represent equal altitude of a mountain, right? And then you can see here is the highest part of the mountain, here is the lowest part of the mountain, and then these lines represent equal altitude. And the rho slope line is a gravitational equipotential line. Basically, around this curve, the gravitational potential have the same level. It is an equal gravitational potential. That means material can flow around this line. But this is also not, this is actually a special gravitational potential line. It happens that you can have many equal gravitational potential lines around each star, but not all of them will touch each other, right? And there is this line that actually touches each other, so that within this part, these materials are bonded to star 1. Within this part, material are bonded to star 2. But if it is on this line, that means that that material can flow around these two stars in a pattern of a number 8, right? So the material around this line, they can go around. At this middle point between the two stars, the gravitational force from the two stars is basically balanced, so that the gravitational potential is equal, so that the material can actually flow over. So this is a special curve. So what happened in the star is that initially the two stars just evolve as you would expect for isolated stars. And star 1 is a more massive one. So it evolved faster. It becomes a red giant first. When it becomes a red giant, it can completely, if it becomes too large, it can completely fills up its Roche lobe. If the star completely fills up the Roche lobe, then material from the star can actually flow through the Roche lobe onto the second star. That star 1 was originally more massive, but when it becomes a red giant, it fills up its Roche lobe, and then it can transfer its material over to star 2. Basically, that because it doesn't take anything, it's just that they're equal gravitational potential, so the material can flow onto star 2, and form an accretion disk around the star 2, and then actually drop on material onto star 2. And this process can be quite efficient. That more and as the star 2 becomes more massive, more and more, as star 1 loses mass, its Roche lobe is going to get smaller. As star 2 gets bigger, it gets more massive, its Roche lobe is going to get bigger, right? So that as the star 1's Roche lobe shrinks, more and more material will have to flow over to star 2. And eventually star 2 can become more massive than star 1. Basically, star 2 is stealing all the mass, a lot of the mass from star 1. It can do that. Okay. And then, so that when the mass of star 2 can even exceed the original mass of star 1. This is what happened in Algol, is that originally star 1 was more massive, but then during its red giant phase, it transferred most of its mass to star 2. And so star 2 becomes much more massive, and then star 1 becomes a white dwarf, so that or a red giant. Now, I mean, eventually it can become a white dwarf as well. But this is, so you see that a red giant star could be less massive than its mean sequence companions. That is because they're very close and some material gets transferred over. So that is the story of the binary star evolution. So you can see in a binary, there can be these very complicated processes. And sometimes if the two stars are so close to each other, they can even form a common envelope that the two stars shares a overall outer body. That is like if they're too close to each other, that one star become a red giant, it can engulf the other star, and so the two stars will become one thing. So there's many of these complicated evolution processes in binaries. So it's much more interesting, but we won't go into that detail. So that is the end of the evolution of stars. So we should now go talk about this bizarre stellar graveyard. Actually, I'm using too much time to talk about those things. Now let's talk about the next chapter, the stellar graveyard, basically the dead bodies of stars. There are three kinds of dead bodies of stars: white dwarfs, neutron stars, and black holes. We talk about white dwarfs today, and then hopefully talk about neutron star and black hole later. What is a white dwarf? A white dwarf is a core of a low mass or intermediate mass star that has died and shed its outer layers in a planetary nebula. As long as the original mass is less than 8 times the solar mass, it will form a white dwarf. So this is the picture of the sun today. When the sun forms a white dwarf, it becomes much, much smaller, right? It's become really, really dense in the center, because basically this is the core of the sun. And then also it is become much denser so it is supported by electron degeneracy pressure. White dwarfs are very, very small. When the sun becomes a white dwarf, it will be about this size, almost the same size as the Earth today. And so that you can see that that is very, very small. But however, in this white dwarf, it can contain 60% of the mass of the sun today. So you see, why did the sun, right now, today we have a lot of mass, and then when the sun becomes a white dwarf, it's only has 60% of the mass remaining. Where does the other 40% go? So Elise answers, where did the other 40% go? When the sun becomes white dwarf, why does it only have 60% left? Okay, good. And now, so most of you have got it, the correct answer. It is B. It's ejected during the right giant phase and right supergiant phase of the sun, which would result in a planetary nebula. That's correct. That the this is the correct answer. Some of you answered A, and that is not going to be. I mean, some of the mass does get converted to energy, but that is a very, very tiny fraction. It's not 40%. It's more like less than 1%. Get converted into energy, or actually more like 0.1%. So it only needs to convert a tiny, tiny fraction of its mass into energy to be so luminous. Okay, so white dwarf is roughly the same size as the Earth, and it is very, very dense, but it's 0.6 times the mass of the sun. And so you can imagine it is really, really dense, right? Density is way, way higher. And 1 teaspoonful of material of a white dwarf will weigh about 1 ton. That is much higher than the density of water or any density that we can have on Earth. Its composition is not always the same. That for the sun, it will become a carbon white dwarf, but actually what composition remains in white dwarf depends on the mass of the progenitor star. So if the star is about the size of the sun, then it will form a carbon white dwarf. If it's a lower mass, it will actually form a helium. If it's a higher mass, it will form an oxygen white dwarf. And that, to understand that, we should think about why the core contraction end. Remember that when the outer envelopes get completely ejected, it stops building more elements on the core, the degeneracy pressure balances gravity, the electron degeneracy pressure, right? And if the temperature is not high enough to fuse the next element, then the core contraction would just stop. So what determines when the core stops contracting is the mass of the star. So in the sun-like star, this is a table that you are familiar with. This is the end of the core contraction in the right supergiant phase, that you have carbon formed in the core, but the core cannot get to the higher temperature to form the next elements. So it ends as that step, and the electron degeneracy pressure balances gravity. So that forms a carbon white dwarf for stars that have the same mass as the sun. However, if it has a much lower mass than the sun, in a low mass star, the core actually does not get hot enough to even fuse helium into carbon. So you cannot actually form carbon in a low mass star. It can even stop before it starts helium fusion into in the core. So at the end of the right giant phase, remember the end of the right giant phase is for low mass stars is always the electron degeneracy pressure already plays a role in there. And that is why we have helium flash, right? When we start helium fusion. But in some stars that the electron degeneracy pressure are so strong that it can actually already balance the gravity, before it can reach the temperature to fuse helium into carbon. So if that temperature could not be reached, then it will actually just core contraction stops at this place and form a helium white dwarf at the end. But you can also say that what about a star that is more massive than the sun? If a star is 2 times or 3 times more massive than the sun, the core can actually get hot enough to fuse carbon into oxygen. So in this place, that it can actually have onset of carbon to oxygen fusion in the core, and then basically go through and the next stage, right? It can have another round of this process, and then it will leave behind an oxygen degeneracy, an oxygen white dwarf or carbon oxygen white dwarf at the end. Okay, so I think this is a good place to stop, and then we'll continue next time and continue to talk about white dwarf and neutron stars and black holes. Thank you for the day. Bye-bye.